Hello, everybody. So this today we are going to be talking about decision trees and random forests. Let's begin our presentation on the next slide. So let's continue with our presentation. So in the first half, we're going to be talking about decision trees. At its core, a decision tree is a supervised learning algorithm, but that definition doesn't capture its elegance. What it really does is divide the world into a series of yes or no decisions. It partitions the feature space into a rectangular region using a hierarchy of questions. For example, is income greater than 50,000? Yes, go left. No, go right. Has the customer churned before? Yes, keep splitting. No, different branch. Each internal node asks a question. Each branch represents an outcome, and each leaf gives us a final prediction. That's it. And yet, that simple structure can solve both classification and regression problems. It can predict whether someone will default on a loan or estimate how much a house might sell for. It turns complexity into structure. In human, as you all know, we love structure. Okay, so let's continue our presentation on the next slide. So now let's talk about the assumptions, okay, the requirements to use decision tree. Now, here what makes decision trees so appealing, okay? They don't assume much, okay? There are not that many requirements. There is no strict statistical assumption like normal distribution, no requirement for linear relations, no need for feature scaling. They handle numerical and categorical feature naturally. But they assume something important, that the relationship between the features and the target can be captured through hierarchical splits. In other words, they assume that the world can be explained through layered decisions. If that assumption holds, they perform beautifully. If it doesn't, well, we'll get to that. Okay, let's continue. Okay, as we continue with this presentation, now let's focus on the pros and cons. Okay, let's talk about strength. First, they are easy to understand, visualize, and interpret. You can literally draw the model and follow its logical step by step. In high-stakes environment like healthcare, finance, public policy, that transparency matter. Second, they handle numerical and categorical data without scaling. You don't need complex pre-processing pipelines just to get started. Third, they capture nonlinear relationship naturally. They perform inherent feature selection. If a feature isn't useful, it simply won't appear in the tree. But here's the catch. Decision trees are prone to overfitting. They can become overly specific to the training data. A small change in a dataset can lead to a completely different structure, and that's unstable. They also struggle with imbalanced classes and noisy data. And perhaps most importantly, their decision boundaries are axis parallel. That means they split along one feature at a time. For complex patterns, they may require very deep trees. Simple, elegant, but honestly, fragile. Okay, for this slide, we are going to focus on application. Despite those limitations, okay, decision trees are widely used. In healthcare, they help diagnose diseases and predict patient outcome. In finance, they assess credit risk and detect fraud. In marketing, they power customer segmentation and churn prediction. In education, they predict student performance and identify dropout risk. And you're probably asking yourself, why? Because people trust models they can understand. If a doctor asks, why did the model predict high risk? You can show them the path, it splits the logic. The transparency builds confidence. But what if we want more accuracy? What if we want stability? That's where we move from a single tree to a forest tree. And we'll discuss that in the next slides. Okay, so we reached the second half of the presentation. And now we are going to be discussing random forests. Okay, a random forest is an assembled learning technique. Instead of building one decision tree, we build many decision trees. Each tree is trained on a random subset of the data, and at each split, it considers only a random subset of features. Then we aggregate the predictions. For classification, we use majority voting. For regression, we average their outputs. This randomness is not really a flaw, it's actually a strength, it's actually a feature of this random forest. By injecting randomness, we reduce variance, we stabilize the model, we prevent any single tree from dominating. Think of it like this. If you ask a person for advice, you might get a biased answer, won't you? But if you ask 500 independent people and take a majority opinion, you get something far more robust. That's random forest, collective intelligence for machines. Okay, so let's continue our presentation on the next slide. So now let's talk about the assumption for random forest. Random forests still rely on decision trees underneath. So they don't impose strict statistical assumption either, but they do assume two key things, okay? The first, the training trees on bootstrap samples. Random samples with replacement will create diversity. Second, that using random subset of features will reduce correlation among trees. And you're probably asking yourself, why does that matter? Because if all trees make the same mistake, averaging doesn't help at all, right? But if they make different mistakes, those errors cancel out. Diversity creates strength. Independence improves assembled accuracy. Okay? So now let's talk about the pros and cons of random forests. Let's talk about advantages first, okay? Random forests achieve a high predictive accuracy through assembly of diverse trees. They are robust to outliers, noise, and overfitting, much more than a single tree. They handle numerical and categorical data well, and they estimate feature importance, which gives us insight into which variable matter the most. But nothing is free. Random forests are computationally intensive. Training hundreds of trees requires memory and processing power. They're less interpretable than single decision tree. You can easily trace one clean decision tree path. And yes, if trees are extremely deep or poorly tuned, overfitting can happen. So we gain accuracy, but we sacrifice simplicity. And now let's end this presentation with by discussing the applications of random forests. So random forests shine in large complex datasets. They're widely used for classification and regression problems where accuracy is critical. They help rank feature importance, telling us not just what the prediction is, but what drives it. They're effective in handling missing data and even detecting outliers. In industries like finance, cybersecurity, healthcare analytics, and marketing, random forests are often the go-to baseline model because they work, okay? And they work consistently. So that's the end of this presentation. Now we are going to be moving on to the to actually looking at the code of the random forest. Okay. Okay, so let's continue with the presentation. And now let's actually look at the code. And this code follow the same pattern, okay, the same structure as the previous code that we have seen. For instance, the first block of code, which is this will be the first block of code. What it does, it imports the libraries that we are going to be using to create the random forest machine learning model. Okay, so we've seen this before, right? We always import the libraries that we are going to be using. Then we move on, okay, to our next block of code here. And what this one does is that it helps us to, first of all, upload the data set, right? Okay, so we upload the data set, and then what we want to see is the first 5 rows of the data set. So it gives us the first 5 rows of the data set and the columns of the data set. Okay, so that's what the next block of code does. And this one follows the same pattern that we've seen before in the other codes. We always import, okay, we upload the data set, and then you want to see the data set. We want to see the first 5 rows and the columns of the data set. Okay, follow the same pattern. Okay, let's continue. Now we are here, and this block of code, what it does is that, first of all, we're trying to understand the data set, right? We're trying to understand it. So it gives us information on the data set. So it's telling us that there are 200 entries, okay? There are about 6 columns. It's telling us that age is an integer, okay? In other words, age is whole numbers. It's telling us that sex, blood pressure, cholesterol, and drug are categorical variables. And it's telling us that Na2K is actually a decimal variable, okay? Then it's looking for these statistics about our data set. For example, the count of age, the count, the uniqueness, okay? Then we have our mean, okay? Of course, sex and blood pressure and cholesterol. You cannot calculate the mean because they're categorical. Standard deviation. Then it's looking for any missing values, and no, we don't have any missing values, okay? So let's continue with our, so then we want to move on to the next column, next block of code. And here, so we convert remember, we have so we have our, remember that we have our categorical variables, right? And computers, scikit-learn, cannot read categorical variables. So we need to change these categorical variables, right? So we change the categorical variables by using labeling. So we actually change, for example, high, low, we change it from 1, 2, 3. Cholesterol, we change it to 1, 2, 3, depending on the number of categories. For example, here's sex, right? So we're going to be doing a mapping, right? Labeling. So female will be represented as 0, male will be represented as 1. Let's look at blood pressure. High blood pressure will be represented as 0. Low blood pressure is going to be represented as 1. Normal blood pressure represented as 2. Let's look at cholesterol. High will be represented as 0. Normal will be represented as 1, and so forth, okay? So we are changing the categories into numbers because the computer can only understand numbers, okay? Then we move on. And now we actually, let's look at the next block of code. The next block of code is going to be printing or creating histograms in box plot. Okay, so let's look at this histogram in box plot. Okay, let's look at what they're telling us, okay? So here is a histogram here for age. And again, just like the other machine learning model, we're looking for outliers, okay? Are there any outliers? Are there any crazy? Even though decision tree, random forest, they're very robust, they can actually handle outliers better than linear regression and logistic regression. However, it can still impact, okay, decision trees and random forests. So we're looking for any outliers. And the same with box plot. Are there any outlier? What are we looking for? The same with distribution here. We're looking for anything crazy, anything that is like out of the ordinary. And so far, everything looks normal, okay? And now this block of code, it creates a heat map. In heat map here, again, we're trying to look to see if the features are correlated with each other. Remember, ideally, what we're trying to identify, we want features that are not proxy of each other, that don't are not correlated with each other. We want independent features, right? However, we know that for linear models, for logistic regression, we try to reduce correlated features, right? We want our features to be independent. However, for tree models like random forest, correlation is not really a modeling problem, but it can impact interpretation. Okay, so that way we know when interpreting the model, we can anticipate any problems, okay? Now, this block of code, we select our features, okay? We select the target variable, okay? In this case, the target variable is drugs, right? And the features would be age, sex, blood pressure, cholesterol. And then we split the data set. Remember, we gotta split the original data set into two data sets. One is for training, the other one is for evaluating. And we use here, in this case, 30% is going to be used for testing and 70% is going to be used for training, okay? Now, we do some scaling here, but in reality, we don't need to do any scaling for decision trees for random forests, but it is included here just for training habit, okay? Just to reinforce the habit of scaling that data. But for decision trees, for random forests, it's not needed. Then we train the decision tree baseline model. Okay, so we do some training for decision trees. Okay. So now let's continue. Now let's focus on interpreting the decision tree classification report. Okay. So let's focus on that one. And let's begin with this one first. Okay, so let's focus on the decision tree classification report and let's focus on class 0. So we have we have a precision of 0.40 and a recall of 0.57. So what does that mean? Here's what it means. Out of 7 actual class 0 samples, the model correctly identified 4 of them. That's what we get a recall of 0.57. It catches a little more than half of the true cases, okay? However, precision is only 0.40. That means that the model predicts class 0 and it's wrong most of the time, to be honest. In other words, class 0 predictions are unreliable. The model is confusing this class with others, likely because the feature pattern for class 0 overlaps with neighboring classes. This tells us that class 0 is not very cleanly separated in the feature space, okay? Okay, so let's move on. Let's move on to class 1, okay? And how can we interpret this? Well, it has a precision of 0.75, has a recall of 0.060. So what does that mean? Here's what it means. It means that the model correctly identified 3 out of 5 true class 1 cases. And that's why we have a recall of 0.60. More importantly, it predicts class 1. It corrects, it is correct 75% of the time, okay? That suggests that class 1 has some distinguishable characteristics, okay? However, because there are only 5 samples, the matrix is unstable. One additional misclassification will drastically change the recall of precision. So while performance looks decent, we must interpret it cautiously due to small sample size. Okay, so let's continue to class 2. So we got a recall of 1.00, a precision of 0.56. The model correctly identified all 5 class 2 samples. So that's actually a perfect recall. This suggests that 2 class is clearly separable from the other based on the features. There's likely a strong signal in the data that allows a tree to isolate this class effectively. However, precision is 0.56, meaning some samples from other classes were incorrectly predicted as class 2. So the model is excellent at detecting true class 2 classes, occasionally, okay? It occasionally overpredicts this class. So let's move on to class 3. For this class, we got a recall of 0.50, precision of 0.67. So what does that mean? The model correctly identified half of the actual class 3 samples. That means that 8 out of 16 were misclassified. Look at the confusion matrix. Many of these were predicted at class 4. This suggests significant overlap between class 3 and class 4 in the feature space. So class 3 is moderately distinct but not strongly separated from neighboring classes. Okay. And let's move on to class 4. Let's look at class 4. We got a recall of 0.48. We got a precision of 0.52. So let's see what this means. Well, class 4 is the largest class in a data set. Okay, it has about 27 observations, yet the model correctly identified fewer than half of its samples. Okay, this indicates that class 4 is highly overlapping with other classes because it is the dominant class. Its weak performance heavily impacts the overall accuracy and weighted average score. In short, the model struggles with the class that appears more frequently in this case, which has 27 observations. Okay. Now let's interpret macro average here. Okay, so let's interpret that. So we have so the macro recall is about 0.63, which is slightly higher than the accuracy of 0.55, in which tells us that the following. It means that some smaller classes are performing relatively well, especially class 2, and that boosts the average when each class is weighted equally. Okay, so let's move on to the next one. Okay, so now let's continue. Let's focus on the random forest classification report. Let's begin with the first class, 0. Okay, so we got a precision of 0.40, recall of 0.57, F1 of 0.47. What does that mean? It means that performance on class 0 did not improve compared to the single decision tree. The model correctly identified 4 out of 7 actual samples, giving us a recall of 0.57. but it predicts class 0, it is wrong 60% of the time, which gives a precision of 0.40. This suggests that the overlap between class 0 and the other classes is structural in the data, not just instability from a single tree. Even averaging many trees does not help much here, okay? Let's move on to the next class. So we got a precision 0.75, recall 0.60, F1 0.67. This means that class 1 performance remains stable. The model correctly detects 3 out of 5 actual classes, but it predicts class 1. It is correct most of the time. Because support is small, about five samples, right? We should still interpret this metric very cautiously, right? However, random forest maintains the same pattern seen in the decision tree, meaning this class has reasonably distinct feature characteristics, okay? Let's move on. Now, class 2, we got a precision of 0.62, recall 1.0, F1 is 0.77. This class is clearly separable. All true class 2 samples are correctly identified, which gives us a perfect recall. Precision improves slightly compared to the decision tree, meaning fewer false positive. This confirms that class 2 has a strong signal in the feature space that multiple trees consistently detect, right? Let's move on to class 3. Precision of 0.69, recall 0.69, F1 0.69. This is where we see meaningful improvement. Recall improved from 0.50 from decision tree and to 0.69. The confusion between class 3 and 4 has been reduced. Random forest stabilization, the boundary between these overlapping classes by averaging many trees. So you can say that this is a textbook example of variance reduction in action, okay? Let's move on to this one. Class 4, precision of 0.59, recall 0.48, F1 0.53. This means that class 4 improves slightly in precision, but recall remains low. The model still struggles to correctly identify a large portion of actual class 4 sample. This is the largest class because we have a recall. It continues to limit the overall performance of the model. This suggests that class 4 is significant overlap with other classes in a feature space, okay? We got an average overall accuracy of 60% compared to decision tree of 55%, which is a 5% improvement, right? So overall, this model, this random decision tree model, does not dramatically change the separability of the data. It reduces instability. Where the decision tree struggled to variance, the random forest improves consistently, okay? That's what it means. Okay, so let's move on. Let's move on to the random forest feature importance. So let me interpret that for you, okay? The most important variable by far is age. It accounts for about 60% of the model decision tree decision-making power. That means that when the random forest builds its tree, age is frequently used in early splits and contributes the most to reducing classification uncertainty. The second most important variable is blood pressure. It contributes roughly about 20% of the model's decisions. So after age, blood pressure helps refine the prediction. Cholesterol and sex have much smaller importance value, under 10%. This suggests that they play a minor role in distinguishing between drug classes. So in practical terms, the model is primarily using age and blood pressure to determine which drug category the patient belongs to. However, we should remember that feature importance does not imply causation. It only tells us which feature the model found most useful for explaining that data. And that's the end of this presentation. I hope you learned something, and I wish you a wonderful day. Take care.